Good morning to everybody. I think it should be morning for everybody here. If it's afternoon, good afternoon from wherever you are. So my name is Edwin Jeru. From the ILEP Africa team here at Student Center, fourth floor. And I would like to welcome you all here for the session on distributed campus computing and the Compute for Africa SU cluster. And I'd like to especially acknowledge that we might be having some of the Strathmore faculty and researchers, a lot of the students who will be joining us from different disciplines within the university, and any technical and IT teams that will be here in this webinar. So this particular webinar would be particularly relevant because it directly touches on how we can access, share, and scale compute resources within the university environment. So just to do a bit of housekeeping, if you have any questions, please use the Q&A tab. I will have my colleague, Mary, who is here, part of this call, Mary Kiongera, who can be able to take note of those questions, which we'll address at the end of this webinar. And please note that the webinar is being recorded so that this particular webinar can be shared to other staff and students alike across the university immediately after this call. So without further ado, we'll jump right into this. So allow me to put a bit of context as to why we are here today. So if you look at Strathmore and a lot of institutions outside there, we have computer labs that are in use during class hours. And after those class hours, the labs are idle, which means the computers are idle as well. We have a lot of students amongst here who have laptops and are not being used to their full potential. We have research teams who need a lot of computing power for purposes of AI model simulations and a lot of data research, inclusive of data processing. And at the same time, a lot of constraints that include budgets that you would find a lot of individuals would face. So the challenge here is not particularly around a lack of computing, but more of a fragmented compute. So what if in this particular case, we could have all these devices, so from our students' devices, from the lab machines, from on-prem servers that are in data centers, or from cloud resources that include GCP, AWS, Azure, all functioning as one unified system. And that is why we are here today, and that is what we are here to explore. So I would like to introduce Dan Desjardins, sorry, I hope I got that right, to guide us through. And just to give you a brief history of Dan, so Dan is a computational physicist and a CEO and co-founder of Distributive. And he is focused on making large-scale computing accessible across highly diverse environments. He works and sits at the intersection of distributed systems, scientific computing, and infrastructure efficiency. He also brings a unique background, having served over 20 years in the Royal Canadian Air Force, alongside experience in academia as an assistant professor of physics and space science. So Dan, welcome, and over to you.
Edwin, thank you very much. And also a special thank you to Dr. Betsy Murithi, who made this possible and connected us. My name is Dan. I'm a computational physicist, and at Distributive, we're building compute economies. Today's objective is to engage with people who need and who use compute. And this is my favorite group to engage with because I'm one of those people as a physicist. Now, over the past couple of months, we've been piloting this technology at Strathmore. And so a special thank you to the leadership at Strathmore for being innovative and trying new technologies. And Edwin said it perfectly. The goal is to capture computers, CPUs, GPUs, servers from devices all over the place and put them to work. And so maybe today's talk, rather than start with a PowerPoint, I'll start right away with a demonstration, like a simple one, and then we'll make it more and more complicated. And then I'll show you some background slides on some of the other things. And then I want to dive into code and API, because the objective for today is to find even just one person in the group that has a computationally intensive workload that they want to run on this cluster. so that we can drive this forward. And the bigger picture is that this type of technology can be brought to campuses all across Kenya, all across Africa, all across the world, to create bridges of compute, to share capacity, but also scientific and AI expertise. So compute is no longer just capacity, it's a bridge for innovation and collaboration. And so I'll share screens. I'll go right into the demo to cut straight to the point. I'll show this maybe over markety looking UI, but under the hood, it's a couple of lines of code that take a workload, a pipeline of functions. In my case, this is just a physics equation. They could be very expensive to perform if they're doing numerical integration or hyperparameter tuning or what have you. The point is, there's a workload that needs to be mapped to a set of inputs. In this rather simple example, it's going to take a 3D function and map it to a grid of points, compute it across a number of machines at Strathmore, and then bring the results back and display them on the grid. And that's it. It's going to use desktops that are spread across the campus. And here I'm sitting in Kingston, Ontario, Canada. I deployed this job, and this is running on computers at Strathmore right now, all the way across the world, and the results are coming back to me. And the job is complete. I have all my results and displayed them here. The use case here is sort of trivial. It just illustrates the idea of distributing a workload from my computer to a collection of idle computers on campus and getting my results. So that's the bottom line up front. Now we'll go into a bit more of a few slides, but are there any questions right off the bat? A curiosity about tapping into the compute that's around us? Feel free to drop anything in the chat. Edwin, feel free to interrupt me and bring the question. I do like or prefer interactive style conversations rather than just talking at people. This here, this is a picture of some of those computers that are on regular desks, across campus. And these are computers running the Strathmore. I don't know if you can see if I zoom in here. That's the Strathmore Crest. Whenever the computer is idle, the screensaver comes on and it's in compute mode. And then it will fetch and accept tasks from students and researchers who deploy them. And then whenever the computer is used for primary purposes by a student, then the screensaver exits and it goes back to being just a regular computer for use by that person. All right, so let's back up and then we'll jump into a bit of a mini slideshow. So what did we all just see in that demo? Under the hood is called DCP, the Distributive Compute Platform. It's designed to take arbitrary computers from across the world and make them work together. It can do that in public groups or it can do it in private groups. Right now, the Strathmore cluster is in a private group where only students and researchers with the join credentials are allowed to deploy workloads there for privacy reasons. But because this software is built on the web stack, which is the same technologies that underpin Google Chrome and Mozilla Firefox and Microsoft Edge, it brings the same security as surfing the web to the compute space. And so it is possible to securely execute untrusted code, which is pretty incredible when you think about it from an arbitrary code execution point of view to be secure, which opens the possibility of computing workloads for nearby enterprises. And so Strathmore could execute workloads for local companies, startups, companies, what have you, and generate revenue. And I'll talk a little bit about that too, because then it becomes a dual-use compute cluster. One, build capacity for internal use to advance research, computing, and AI. Or two, generate revenue by monetizing that cluster externally. So a little bit of background. This was my office several years ago. I used to fly C-130s for search and rescue in the Canadian Air Force. And then I later taught at Royal Military College of Canada as a professor of physics and space science. And that's where I did a lot of research and needed a lot of computing power, but was frustrated with how complicated it was to get access to that computing power. So much so that what I did was I wrote my physics code, I put it on a USB key, and then I used that USB key on 20 computers, and then I would just launch the same code on the different computers, but change the loop indices. So on one computer, I'd compute from 1 to 100, and the next computer from 101 to 200, and so on and so forth. So I manually distributed my job by walking around computer to computer with my USB key with my code. And the dream is why is Kubernetes and all these other, applications so hard for a physicist or a chemist, or any applied user to set up and run? Running code on one computer is straightforward and easy, but the minute you want to run it on more than one computer, you want to run it on two computers, now you need to package your code in Docker and use Kubernetes and manage it. Or if you're going to use the cloud, you have to set up the right instance in the right region with the right operating system, with the right drivers and the right dependencies and configuring environments and then secure. Like it turns into a maze. If all you want to do is take, your workload, your for loops, and then spread them out across a couple of devices, it should be easy. It shouldn't be difficult. And so that was the dream that we wanted to solve. And so founded in 2017, 8 years ago, we're currently a team of 15. Our CTO, his name is on the Mozilla Monument, in San Francisco. So he helped build a lot of the standards that people use today and maybe even take for granted that allow the web to operate free and secure. And we built that dream computing tool that would harvest compute from devices all around, but more importantly, make it really easy to use without all of the DevOps steps and hoops to jump through. And we built in the ability to meter compute by and between different, computers, but also organizations full of computers. Because if you can meter, you can charge and generate revenues from commercializing that compute. So the objective sort of shifted, or at least got a little bit bigger. Don't just make compute capacity abundant and available and easy to use, but make it work for people. Create compute economies where, in Canada that we say like, we'll keep compute money in Canada for Canada. In Kenya, keep compute money in Kenya for Kenya. Right now, obviously a lot of data centers are being built all over the world, and they're soaking up cash. In this way, there's a little bit of pie for everyone. And so underneath everything, DCP, it sounds like TCP/IP, and that's on purpose because it's a compute technology built on web standards, which allow people to surf the web and execute untrusted code securely. Well, imagine a compute platform made out of those same capabilities. It runs across every operating system. We just finished an Android worker, for example, that needs to be added to this list. It runs on standard Linux computers, Windows computers, and interestingly, it'll run directly in the browser where you don't even need to install anything. I can talk about this. I want to get back into the technical stuff given the audience, but really quickly, what does it mean that it's built on the tech stack? Well, it can run anywhere on anything, and I'll get into a specific set of examples where we're even doing compute on fridges. So compute on everything, everywhere, all at once. From fridges all the way to cloud and campus computers and everything in between. CPU and GPU, same code APIs, but will run across any platform. Doesn't matter what the operating system is. It just runs everywhere securely all at once. Sovereign compute economics. This one is the closest one to my heart. This goes right to building economies. Right now, there's a big advantage for the hyperscalers who are basically soaking up all of compute demand and compute capacity and then selling it to the world. We see a vision where that still exists, obviously, and where it interoperates with cloud, but there should be space for running compute within dispersed individual organizations who they as well get to participate in the compute economy by selling compute capacity and for them to consume and to sell to externals so that it becomes a big pie that can be shared with everyone. And then finally, trust by design, built on the same technologies that allow us to surf the web without fear of being compromised, as long as you don't download anything. Obviously, when you're surfing the web, if you're just surfing the web, it's extremely secure. And that's because billions of dollars over the last 2 decades have been put into making web infrastructure able to support secure, untrusted code execution. So a compute platform out of that benefits in the same way. So this is now we're finally at the technical stuff. So if everyone has been interested so far in the audience, the call to action is embedded in this page. Basically, if you have a computationally intensive workload and you want to try this cluster, because we want you to, because we want to build from here. We want to expand the cluster. We want to bring it to other universities and colleges, locations with even less compute, and then share compute and build capacity together. If you have a workload that in some way looks like the code on the left, where there's either a for loop or a nested for loop, a multi-dimensional parameter sweep, or a batch inference, or what have you, somewhere where you're applying some function or pipeline of functions to a series of inputs with a bunch of arguments, and you're getting those results back, it can be rewritten as what you see on the right, and it will automatically distribute across the Strathmore compute cluster. And we will help you with that. We want to onboard use cases. So again, anyone in the audience with a distributed computing use case, or even just if you're not even sure if it's distributable, ask us and we will work with you. But basically, if it kind of looks like what's on the left, we can help rewrite it to what's on the right and run it on the Strathmore cluster to then build and scale. Then we want to hear from you. So what are examples of distributed workloads or distributable workloads? Well, just like that API example, this is the same representation of that API, but just with pictures. If you have a series of inputs, which don't have to be scalars, they can be lists or arrays or images or blobs of data or MP3s or PDFs or basically any enumerable set of inputs. And then some function, which can be as complicated and expensive as you like, that maps to all of those inputs to generate a set of outputs. The distributed compute API will automatically take that function and those inputs, spread them out to the Strathmore computers in the cluster, and then reassemble the outputs or the results the same way that the inputs went in. And it'll do that in line within the code. You don't have to do anything special. It's all within the script. This means you can run any type of Monte Carlo or statistical modeling, and Monte Carlo analyses are used all over the place in finance and insurance for portfolio modeling and what have you. Monte Carlo modeling all over the place. Parameter sweeps. My physics example was an example of a parameter sweep where I was doing numerical integration across a parameter space to generate plots and curves and things that demonstrate or that explain voltage induced in an antenna given the communication between a sonobuoy and a satellite. Enterprise batch jobs. Examples would include optical character recognition, turning scanned documents into digital searchable text. Another enterprise batch job would be applying small LLMs to that digital text to then structure the data, right? Another one would be machine vision, right? Or what have you. Data transformation, image processing, rendering, there's a whole bunch of distributable workloads. What is not a distributable workload? Anything that is MPI in nature. Why? Because that would require internode communication, and for security reasons, right now we're not allowing lateral communication between computers on campuses because it's more secure not to for now. And then as we go forward, we do see a future where we'll open that up. Right now, we're going to perfect everything on the distributed side before we start implementing MPI. Implementing MPI in distributed networks would also have some drawbacks because you'll be limited by the underlying network. And so this one will proceed with caution as we implement it. But right now, there's more than enough workloads that are distributable that we'll focus on before we bring to the world this MPI stuff. So unfortunately, what this means is that training neural networks, which you truly do need HPC supercomputers for, is not something you can do on a distributed computing platform like DCP or something else. But once you have trained networks, then you can deploy them and operationalize them. And I'd love to be able to do training on this. We can do some types of classical machine learning type training, like distributed random forests, or XGBoost, or bagging, or linear regression, or those types of algorithms. But PyTorch, deep learning, for example, is not something that can be done right now with this technology. But operationalizing the models that do get created are. So if people train models and then want to operationalize them for companies and generate revenue, that can be done right now on this type of system. Anything with finite element analysis, where you're doing domain decomposition and communicating intermediate results between nodes as you're doing simulations, again, is something that would need MPI. So very quickly, these are the things that this does right now. These are the things that we'll do in the future. We don't know when. Still working on it. Here's an example, a real applied, serious government example of where this technology is being used right now. It's a Monte Carlo simulation for modeling Royal Canadian Air Force pilot staffing projections. And deep down in this code, and right in the top, you can see this is Department of National Defense. It's an open source GitHub profile, so I'm not sharing any code or anything that I'm not supposed to here. Disclaimer. But right at the bottom of model.py, you can see there's that little for loop for n in range, of reps. Run the Monte Carlo simulation and save the results. And behind this, there's a big model, Monte Carlo model running, and it is computationally expensive. And if they want to run this for like 10,000 reps to capture rare event and have a good idea of what the future could look like in terms of staffing levels at the different squadrons across the Canadian Air Force. And that's a perfectly distributable example, because each of those reps can be distributed to a different machine, and then the Monte Carlo simulation is run in parallel, and then you combine the results at the end. And so this is what that code looks like on DCP, but this is all of the code. Like, I'm not hiding anything. This is all of it. This is all it is. The reps are the inputs. Okay, so this is up to 10,000. The job takes the build and run model and any inputs or arguments and maps it to the reps input that we just defined. That's the job. And then configure the job. We're giving it a name. That's optional. I mean, it's just good to give it a name, because then the workers will see what they're doing. I'm putting into a compute group. This is going into the demo group, but this is where I would replace the join key, and I would type in a join secret via command line as a flag to enter the Strathmore compute group. I can upload into the virtual file system modules, any number of modules that are required by the job. And additionally, I'll make it require any of the NumPy, SciPy, Pandas, scikit-learn, whatever. And so the workers in the Strathmore compute group will self-configure with any of the standard modules required by the job and any of the custom modules that I'm uploading myself in real time to do the job, and then it will forget them and move on to the next job. So from an IT perspective, Once these workers are deployed, Strathmore doesn't have to do anything to configure drivers or upload dependencies or any of that stuff. They self-configure automatically on a job-by-job basis. Then event listeners, there's more. I just included 4 here, but when the job's state changes, print it to the screen. When the job's accepted, print the job ID. If there's an error, print it. If there's a result, print it. But obviously, you can wire in anything. Like if there's a result, check to see if it's better than the last 10 results. If not, ignore it. If better, then replace them. Or, when it finds the best result, send me an email. Or, there's all, you can wire up all kinds of stuff. Or when the job completes, take the 5 best results, mutate them, and then send out the next level of job. And anyone in the room would know that that sounds like a genetic algorithm. And so you can chain jobs together like that. And then you can launch the job just by calling job.execute and results equals job.wait. And that's it. And so notice here, this is in line with the code. Like it gets injected right into any Python script. We have Node.js equivalents. We have web application examples. That was the first one I showed you with the fancy plot. So right now, people can write jobs in Python, in Node.js, and in JavaScript directly for web browser applications. Demonstration. So I did one earlier. I'll rerun it now that we have all that context. So, I mean, this will be quick, but then I'll show something else. So behind the scenes here, this is taking my math function. It's putting it into the Strathmore Compute Group. It's giving it a name. I'm using an API key so that I can see and manage my job later. It's using a payment key so that my compute credits that I earned when I ran my workers then get debited with the job, and then they end up in the workers doing the work. So Strathmore is going to receive compute credits that I am deploying to run this job. And then I'm defining other, job inputs, the arguments like the domain that I'm computing this over, grid size, and what have you. And then deploy job, and then there's a little console here. And so job ID is printed, so that's the state. And now I'm getting results back. Job.exec was called behind the scenes, and now it's results equals job.wait.
Hello, Dan.
That's the
Do you
Python
mind
input.
increasing your screen just a bit? I think the font is a bit too small.
Yes, and of course, any of these things are like all of this is shareable. Everything you've seen, if people want these examples, they're online, and we can share all this. Okay, a little bit more serious example here. So the physics example that I showed, this is what a physics Python job looks like. So at the very top, import DCP, dcp.init. From DCP, import wallet, and this allows you to configure an identity and an account from which compute credits will come out. The workers doing the job receive compute credits, and that's how you create a compute sharing economy where it can go round and round. The input set, in my case, I'm using a range object here. I'm calculating a bunch of frequencies from 50 to 300 megahertz by steps of 50 megahertz. And then I have a big old expensive computational function. This function, V for voltage, will apply to a particular frequency, which is in my array of frequencies here, a list of frequencies. These are just a bunch of arguments that are, in this case, are static. This one's dynamic. And then I'm importing all my functions from the libraries I need. And so SciPy, all these Bessel I and K functions and numerical quadrature and what have you. And then all my code. So this is my fancy physics code. It's not relevant to distributed computing. It's just my code that I wrote. And you can see, again, we're going to go by this, but this is a bunch of math. It's a bunch of math. Towards the end here, look at this. I'm doing a lot of numerical quadrature, which is very computationally expensive. I'm integrating over 3D volumes over all space. And then I'm calling progress in between each of these integration efforts. And then the function basically returns the sum of the voltage induced in that antenna element. This is the antenna example I was talking about. Here are the arguments. So here are all the other arguments in that work function except for the frequency. This is the job. So the job takes that function or that pipeline along with arguments and maps it to that list of frequencies. And it will do it in parallel. Configure the job. And so here I'm telling it what modules it needs. I'm putting it into a particular compute group. I'm giving it a name. I'm giving it a description. I'm giving it a link, so people can see if they want to see. This is all public, optional public information, job information. So people can then go on your webpage and see what you're up to. If you have like a page describing your research or you as a researcher. Wire up some event listeners. Here I got a bit more fancy. So I have a progress bar instead of just printing, just each result. It's just going to show a progress bar. And then I just do job.execute. And then I get my results. And once I have them, the rest of this just plots them. So I ran this on the Strathmore cluster, and this is what it looks like. I believe there's 4 computers that were accepting slices of workload. This is a visual representation of that job as it just ran. And so you can see each of these slices took about 7 minutes approximately. So if you have 1,000 slices that each take 7 minutes, that's 7,000 minutes of computing time. That's a long time for one laptop to run. But if you have 100 computers, like all the computers on campus, or even better yet, if there's 10 universities across Kenya that are pooling their compute and because they trust each other and they'll run each other's code securely using DCP, then you can see how that things would go a lot faster. And you can even see it just with like 4 computers in this plot. You can see they're all working in parallel and they're doing it in chunks. And so the total time is much less than if just one laptop was doing it. And then to make things a little bit more fun, here are the outputs. I'm going to zoom in here, and this is where we're going to talk about money for a little second. I ran this same benchmarking job on AWS. And you can see the benchmark time to run those slices on average is about 5.8 minutes. And if you were to, and I was charged by AWS 18.73 cents per hour to run that workload. And so given that the Strathmore computers, the specific computers that were used on average took 7.3 minutes, that means that they're executing at a speed of about 80% of the AWS speed for the same workload. So 80% of that 18.73 cents is 14.88 cents. So if you scale, okay, if you scale the compute to the performance, because at the end of the day, what people care about, they don't care about, well, I mean, some people care, but most people don't care about operating system or region. I mean, maybe well, there's lots of reasons to care, but let's just put it this way. For me specifically, as a physicist, just trying to do research, I just want my results. Whether it's a C6GX large or a Raspberry Pi or a fridge, or I don't care. Just get me my results. And so the only thing that matters to me is my results in time. And so as a researcher, I would deploy my job, and I'm willing, look, like either I wait to Thursday or I pay $3 and I have it done by noon. That is the kind of idea. And that money goes to other schools. And then if I'm signing up my computers to do work for other people, then I get those compute credits back. And then you can create circular compute economies where there's compute sharing. Or you can pay to burst to the cloud or wherever else and create hybrid compute economies that use everything. But anyway, this gives people a bit of a flavor of how you can benchmark the value of compute, the compute you have in your own house, in your own university, and give it a monetary value compared to other places you can run the same workloads and then benchmark it. Okay, so I think that's the demo. Cognizant of time, there's 20 minutes left. I'll wrap this up in about 5, and then I want to jump into conversations. So that's more than it's more than just the demo. I think we went really deep there. So what's the big picture here? Well, it's free for Strathmore to use on campus. In fact, it's free for any university or college to use on campus in their own environment. But if they want, they can turn around and sell that compute capacity to local organizations, enterprises, or other institutions, and then generate revenues. And then that's where distributive takes a little piece. We give 80% of the revenue to the organization, and then our piece we reinvest in our team to build more tools and bring more capabilities and innovate the HPC stuff and what have you. But there's an even bigger call to action or cause here. Strathmore can team up with local colleges and universities, maybe universities and colleges that have less compute available to them, and then be a leader in terms of bringing compute to the underserved, right? Can even connect to a global compute fabric. And then creating not just, okay, sure, we can create compute economies, but it's also a compute movement. And I was talking about collaboration earlier, and I say this from the bottom of my physicist heart, that more research and more capacity sharing in the world is going to make the world better for everyone together, and not just the Ivy Leagues who have all the cash and all the compute. The compute continuum. Okay, we've been convinced that there's only edge or only cloud, but that's not true. Everything can do compute. And this type of technology can stitch all that together and turn it into a single fabric and interoperate. I hope no one got the impression in this call that I'm trying to offer a pure alternative to cloud, because that's not true. It's totally complementary and interoperates with cloud and on-prem and both. And as an example, just to be funny, what you see on the left in this little video is a fridge doing physics. And what you see on the right is a Tesla car doing physics using DCP. And obviously this runs in the cloud and it runs on campus. So it is true that you can create computing clusters out of anything. Here's a VR headset on the left. And on the right, this is a smart board, and those educational display boards that exist in classrooms all over the world. They too can do compute. They have 8 cores and a GPU. That's a lot of computing power. There are workers for any operating system, any device. We can talk about security architecture. Like I'll just blow through this, but basically at the heart of it, it's running V8 and Google Dawn for CPU and GPU workload execution, compartmentalized, isolated, no I/O, with the hard drive, so totally safe to run in a sandbox environment, and it runs anywhere. Browser workers. So not only can we run on these screensaver workers that I showed at Strathmore, but the workers can also be embedded directly in web pages, which means that you could embed this worker in youtube.com or even Strathmore's homepage, and anyone on that web page, anyone on youtube.com or on strathmore.com, for example, would become a worker in a cluster. This could create completely brand new business opportunities where you can replace web advertising as a source of revenue, right? So think of it this way. YouTube, whenever someone uploads a new video, that video has to be transcoded, okay, from whatever the raw input format is to 480p, 1080p, 4K, 8K, and then all the different codecs, etc. Well, that's happening on GCP servers right now, right? Well, that means those servers are not doing other stuff for other people, and that's why. So they're sacrificing revenue in order to transcode new content to keep their viewer base fed with new stuff. Well, you could actually shift the transcoding workloads onto the people who are passively watching YouTube, right? In exchange for not having them see ads or a free YouTube Premium, or an offset YouTube Premium account, because they're doing compute in the background, which frees up capacity to do other valuable things like crunch numbers for Goldman Sachs. And that's the YouTube example, but it's true for newspapers. It's true for like online newspapers. It's true for Vimeo, TikTok, whatever. Wherever there's online communities with viewer bases, they could opt in to compute to offset ads, to get rid of ads, and have a better experience. So we're very excited about that new advancement in the world of compute. No, you can't do that with Kubernetes. Kubernetes doesn't run in the browser. And that's it. So what are we doing? Well, we're in lots of academic institutions and hospitals now. Hospitals can predict KPIs and optimize schedules. This is a distributed random forest training example and an inference. You can do batch OCR for insurance, for example. Government of Canada just purchased $100,000 worth of these DCP compute credits. So it's getting serious, and we just partnered with an international OEM to operate a compute platform globally to bring compute even wider and faster. And so we're partnering with academic institutions like Strathmore to test the cluster, but we want to go big. We want to enable compute sharing in Africa, in Australia, in everywhere. So here it is in Canada. These are libraries and campuses full of computers that are running compute. This is Africa Nazarene University. This is Australia. They have 200 computers doing work over there. This is in Brazil at a hospital. And this is as of just yesterday, Strathmore University, where there's computers, creating clusters that are usable. And so that's it. The call to action. Again, I want to answer as many of your questions as possible right now, but what we really want, tell all your friends, tell all students, tell all researchers, what we want right now is an actual real workload of yours to distribute on this cluster. And we'll work with you. We'll adapt whatever code it is, and, tweak those couple of lines and make it work. Because once it works, then we can get a second and a third and a fourth, and then people can just use that compute capacity, do more research faster, but then turn that into press releases and maybe go to the World Bank for, and put on foot a digitization project and go get grants and point at it as evidence of a viable way to create compute capacity all over the world and so on and so forth. But it all starts from having proof points, which means that we need people with a real use case from within the audience and beyond. Step forward. Tell us about your use case. Let's run it. And let's make an example. Let's put it in the news. Let's use that example to go get grants. Let's build and scale this and build tools. And there's even an opportunity to then sell that compute capacity and generate revenue for Strathmore and beyond. So that's the call to action. Thank you.
Thank you very much, Dan. Much, much appreciated. I believe everybody has been able to pick a thing or two from whatever is explained to us about distributive and computational capacity. And just to say from my part, it's quite interesting to see that as long as a device has CPUs or a bit of RAM or a bit of GPU, you could actually be able to now use it and have a bit of computational capacity utilized towards solving problems. So in this particular case, for students, it would basically mean the access of compute environments that would otherwise be out of reach, especially if we're looking at it from a cost implication. If you're looking at the researchers, it means reducing dependency on single infrastructure sources. So if you're talking about GCP or AWS and the high cost that comes with it, it means you can be able to use these kind of devices. And even at the university at large, it introduces a model where existing investments are better utilized. So instead of having idle machines seated around the university throughout the day, throughout the evening, they could be utilized to earn a bit of extra income for the university. So Dan, I'm just going to put out a couple of questions, and to the audience as well, please ask your questions. But I do have a couple of questions for you. So from an institutional perspective, so in this particular case, Strathmore University, how would you say that we approach this idea to the management level about whatever we're trying to showcase or whatever we're trying to introduce here?
So the management would be like the vice president of research, the VPR, for example, or the CIO. There's different stakeholders at the management level, and there's a different way to approach it with each of them, of course.
Okay, let me just rephrase. So we have what we call a research and innovation sector within the university, and we have a deputy vice chancellor that is in charge of that. So if you were to approach him on how to look at this particular model, what would you say about that?
So when we're engaging with the research staff, it's all about researcher enablement. The sole job, or one of the many jobs of the VPR, the chancellor at a university, is to make sure their researchers have equipment and capabilities that allow them to do their research. Because the more impressive their research can be, the more competitive they are, and the more competitive the university is, the more they can attract grants and students. And it's just better, right? You want the best possible researchers at your university, and for them to be the best, they have to have capabilities, infrastructure, laboratories. It doesn't have to be just compute, but I mean, you have to have good labs, with good equipment to be able to do whatever computer engineering their stuff they're doing. So compute is an asset that allows researchers to be competitive. And so when we're talking to chancellors and VPRs, it's all about compute enablement for their researchers in their pursuit for excellence and competitiveness. The pitch or the presentation or the argument changes when we're talking to the CIOs, because a VPR will say, well, that's good. I want my researchers to have as much compute as they can because they'll be as competitive as they can. But then the CIOs get brought into the conversation, and all of a sudden it switches from a tool to security. So that's the two-sided approach. One is the capability and the competitiveness, but the other one is then the security. And so when we engage with CISOs and CIOs, we would explain that this compute platform is under the hood, is built on the same technologies that underpin Chrome. And so every university campus, every computer on those campuses are already running a web browser, right? It would be hard to find a university computer that doesn't have a web browser installed on it. Right? So by default, those computers are already running the technologies in the way that DCP runs them. And so if a CIO were to not trust DCP and how it's executing code and everything else, they should uninstall all the browsers immediately, because it means they wouldn't trust the browsers. That's a it's not a hand waving argument, because under the hood I have lots of technical documentation, but basically it's the same security profile as the web. And if they already run the web on their computers, then it's a model that they can understand and feel comfortable with immediately in terms of this compute. So that's the approach to the VPR and CIO, the security and the enablement. However, there's one last element to this. They'll always ask, show me some case studies. Okay, that's the final thing. So the vision is good, the security is good and convincing, but then the last thing is people ask for, okay, what are the case studies? And so now we have a whole series of case studies. I was just showing some cost comparisons and benchmarks and everything else from other workloads, but the best case study in the world, and that is one that comes from in-house, right? And so that's why in this audience, if even a single person has a workload, that whether it's one they already have or one they want to develop, if we can bring it on and then run it and then use it as the case study, then you have the perfect trifecta: the vision, the use case and outputs and benefits and quantitative everything, and then the security discussion. That is a package that goes to university management to then launch the next phase. What is the next phase? Well, it's expanding the cluster, and then it's co-applying, for example, maybe for grants or the university alone, getting more use cases, then going to other universities, and then reaching out to local enterprise, and then onboarding their use cases and generating revenue. And there's 50 million directions, and one of them is just consuming internally. If a university just wants to consume their internal capacity with researchers and students to be more competitive, it can stop there, and that's totally fine too.
Awesome. Great. Thank you for that. Thank you for that. So I can see we have about 4 minutes left. So any questions that the audience might have, please, you can go ahead and ask questions. I can see there's a comment here by Brian in the comment section, in the chat that is. So he mentioned that this is very interesting. I'm not from tech, but I gather this would be like Torrents. I have a startup in Strathmore that does work with small businesses, and to run the workload, it gets very expensive with AWS and GCP. Wondering what I could use this for, especially for data analytics. What are your thoughts?
I will pull up a slide that was in the presentation at the very beginning. anything that looks like this. On our website, distributive.network, there's even a tab called suitability on the top right that will tell you if a workload is suitable for distributed computing or not. But in a nutshell, if they're doing data analytics, depending on what that data analytics is, most data analytics, the only thing that we don't do right now is training neural networks. We can train certain types of algorithms as long as they're distributable, basically, as long as they don't require MPI, again, random forest, bagging, linear regression, etc. So as long as it's not computational fluid dynamics, finite element analysis, or training neural networks, it can be distributed. And so if you have a startup that's, running workloads, here's an example of an equivalent framework, Apache Spark or PySpark, which is the layer on top of it. Banks use that a lot, right, for their analytics. This is pretty equivalent in that you can express a workload, spread it out, and get the results back. So if your startup is running a consultancy that's working with a whole bunch of enterprise customers that are doing analytics that are expensive to run, that would be perfect. I would love to work with you to canvas them to find out which workloads are suitable, because those are the types of workloads that could be executed on Strathmore's cluster, right? And so what's the win-win-win triangle here for everyone? That those enterprises would get cheaper compute, maybe half, maybe a third, maybe a quarter of their current spend. And what they do spend ends up, or 80% of it ends up in the hands of Strathmore, right? And it's creating local economies. So the fun here is you can reroute cloud compute spend to local universities and colleges where the money will be put to use in the institution. So growing capacity locally, creating economies locally. So let's please reach out. Absolutely, because that would be a stunning use case to present, management. And so, Dan at distributive.network or contact Edwin or anyone within Strathmore. So, we can make this happen.
Awesome. Thank you. Thank you, Dan. I can see Mina has raised his hand or her hand. I'm not entirely sure. So, Mina, please go ahead. I've just unmuted you. You can unmute your mic. Sorry. Mina M.
Just to confirm, can you hear me?
Yes, you can hear you.
Fantastic. Firstly, let me apologize for the noise in my background. But this is a fantastic presentation, Dan. I would like to find out specifically around the modularity of the distributed compute infrastructure itself. So I'll just give you a bit of context as to my use cases or my reasons. I'm currently running something called the Udara project. This is one of the largest AI educational initiatives across Africa right now. And so we're currently in about 167 universities across the continent. And we have Udara campus chapters that are being set up in each one of these different institutions, right? Strathmore is one of them that we're currently trying to set this up in. And we will have research lines that we're going to be running through each one of these institutions. And a lot of this research is also going to be cross-border research. So to give an example of something that's existing right now, here in Kenya, we've been having an issue with flooding in Nairobi and in a number of different areas. Something similar we found out is happening in Ghana, in Accra, and in a few other states within Ghana. And so we have a research line and team in Ghana, as well as here in Kenya, and some other people in Nigeria that are working towards creating solutions to, one, be able to predict some of these rains or seasonal shifts, and how we can be able to now warn people or create advisory systems for something like that. Now, you had mentioned that something like training neural networks, etc., is out of scope at this point in time. But now for various use cases for this research line, as well as for other ones, how possible is it for us to use the modular infrastructure across multiple institutions or across multiple countries? Thank you.
Great question, and it's purpose built for exactly that. And so one of the demos I didn't show today is sending a job simultaneously to Australia and Kenya and Canada. In fact, let me share my screen. Because this is cool. I want to show you how easy it is and modular from that perspective. So remember earlier I was showing this physics code. this is the code I wrote. Okay, so it's kind of moot. What it is doesn't matter. It's more the form of the API that's important. But this line right here, so my job was this. I took my analytics, and for your purposes, maybe it's, okay, everyone's trying to do neural network, but you can do machine learning and tabular, like good old-fashioned machine learning. XGBoost and random forest is better, I think, on tabular data anyway, because it's explainable. Neural networks don't really tell you why they did what they did, but that's a different conversation. Not everything should be a neural network, but again, that's a different conversation. Job equals compute.for, you map like your analytics function with your arguments to the input data. Okay, good. But down here, in terms of the modularity, I'm attaching that job to a particular compute group. Here I'm attaching it to the IBM compute group. But this is a list. And so if I want to send this to multiple compute groups, I just do this. And so if I were to, and by the way, never hard code a password in a script. This would just become, you make it a flag where you pacify the command prompt, but that's besides the point. That's IBM, Strathmore, UniSQ, and Queens U. This job now will simultaneously go to IBM, Strathmore, University of Southern Queensland, and Queen's University. So this is across USA, Kenya, Australia, and Canada. Each of these locations, each of these compute groups have workers at those locations, and they will all pull the job. Another piece of API I didn't show is that you can have each of these workers polling local data and not just data provided by the job deployer. And now I should pull up where this becomes relevant, because I think this is going to fall close to your use case. I need to organize based on date added and go to the most recent. Group by, I don't care about kind, just the most recent. I'm not going to find it. No, I will find it. Let me take the time, because I want to show you precision medicine in a modular way, which is not far from what you're asking for. The use case is different, but the architecture, the topology is exactly what you're asking for. Okay, here we go. Sorry for that. I'll clip that from the recording. So this is a presentation we did on precision medicine at the Data Analytics for Healthcare conference in just this past December. It's a collaboration between a couple of different hospitals. UHN is the biggest in Canada. And we're talking about rare diseases and treatments and everything else. And we get into federated multiomics computing. And so right now, the idea of putting genomics data in the cloud to then train models, ML models, is expensive. And getting that data out of the hospital is not really easy to do because of sovereignty and data privacy and everything else, especially since it really is the definition of patient data. So instead of bringing the data to the compute, bring compute to the data. So this is where DCP is deployed in the hospital. So you have computers in each hospital that they can work on local data sets and push only results upstream. So they would push up like these submodels, and those submodels can be aggregated in a federated learning approach to create aggregate models. And then those models, there's extra fun stuff here, but those models can be annotated with the relative contribution of each hospital. And then when those models are used to perform inference, to do precision treatment, for example, or whatever, or treatment selection, you can then create royalties from that inference and then pay all the hospitals proportional to their contributions. So it's like a royalty model for AI, where independent parties that come together to create these aggregate models without giving up any of their data can then receive pro rata royalties based on those models. So it's kind of what you remember Napster. If you remember Napster, they just ripped music from all over the world and gave nobody nothing, and then they got shut down eventually. OpenAI stole everyone's data, right? And nobody gets credit or attributions or royalties for the OpenAI models. But then, to continue my music analogy, Spotify came along and said, okay, well, we'll charge our users something to listen to music, but will pay, revenue streams, royalty streams to the artists. And because they had a legal framework and a morally, ethically correct one, financially aligned incentives, now they dominate. And so imagine a world in which AI model training has the same sort of built-in fairness, royalties for the originators of the data and compute, in the same way that music, have the artists are the originators of the music, they get royalties, and that's what sets up fairness and everything. Same thing here. And so once that model is trained, then you can redeploy it to all the hospitals to do that precision inference for treatment selection or what have you. Sounds to me like your use case where you have multiple institutions working together to run analytics on data sets at each location, and then you're pushing results to a common location or sharing it, redistributing it to everyone for a common awareness. It sounds exactly the same. So yeah, happy to I mean, that would be a complicated but excellent use case to pull in more institutions to participate.
Thank you very much, Dan. Mr. Maina, I hope that has answered your question. I can see you're on mute, but I hope it does. In case of anything, you can just reach out to us and then we can just progress the discussion further. So because I can see we are over past the hour, I would really want us to close this particular session. And I am putting a link in the chat. So this particular link is to request you to participate on a distributed computing experience. So basically, you can just fill in your details and then you'll be selected when it comes to running pilot workloads for this specific purpose. So please go ahead, forward this to your friends and colleagues, and we see what we can do together, especially in using our resources that we have within our SU environment. So just to close us off, I would like to thank you very much, Mr. Dan, for the session. Thank you, everybody, for joining. And we're at a juncture where there is a real opportunity to empower students to access compute. We have researchers who can have their research and innovations accelerated. And obviously, for the university at large, we try and see how best we can add value towards the existing resources. So thank you very much, Dan. Thank you very much, team, from the students to the staff and researchers. Thank you, everybody, for joining today. And I wish you all a very fruitful day ahead. So Dan, any final words before we close, as we close?
Asante sana. Asante sana. Thank you very much.
Awesome. Thank you. Awesome. Thank you very much, guys. Have a good one. Thank you very much.
Bye.
Bye-bye.